Welcome back friends. Good morning to all. We'll continue this machine design, this chapter number 1. I am not a professor, I am not a lecturer, I am not a teacher, I am a self-learner. I want to share my knowledge to my juniors by self-study. The self-study, the best study in the world. So friends, this is the introduction. This is chapter number 1 and we are continuing. We are doing this is lecture number 3, introductions. We'll recap friends. We did the general procedure of the machine designs. We have studied last lectures, and types of load. We studied the static loads, the steady load, the dead load, live loads, and the suddenly applied loads. Impact load you have studied, and the dead load, a load is said to be dead or steady when it does not change its magnitude or directions. Magnitude and direction will be constant over a period of time. Then that is called the steady load, or that is called the dead load. And we know that live load also we studied, that a variable load. The load is said to be live load when it changes continuously, means its magnitude and direction will be changed continuously. That is called live load, or that is called the variable loads. And the suddenly applied load also is studied. A load is said to be suddenly applied, or that is called the shock load. When it is suddenly applied or removed, you have to suddenly apply and remove, then that is called suddenly applied, or that is called shock load. And the impact load, a load is said to be impact load when it is applied at some initial velocity, then that is called the impact load. The machine parts resist the dead load or more easily than the live loads, and more easily than the shock loads. Okay. And also we studied that what are the stresses. Stresses, we know that when some of external force act on a body, and the internal forces which is equal and opposite will set off inside the body, and that will resist the external deformation. That internal forces for a unit area is called the stresses. And the stresses, it is also stress. The stress may be the tensile stress or compressive stresses, or maybe shear stresses or bearing stresses. That is depending upon the type of load applications. And also we know the tensile stresses. When a load is applied on the body, it will elongated. The stress will develop in such a bar is called tensile stresses. Tensile stress is equal to P by A. P is equal to upon Newton, and area is equal to mm square. The Newton per mm square is the unit of stresses. And strain, when a body is when a system forces or load it act on the body, it undergoes some deformation. The deformation per unit length is called the strain, and the strain is equal to del L by L, and L is equal to, suppose mm change in unit length, and the original length is equal to mm. You will do this one. So strain has a no unit. Unit of stresses already told Newton per mm square, or that is MPa also we are telling. MPa is equal to 10 to power 6 Newton per meter square is equal to you can also Newton per mm square. That is conversion already we studied last lecture, and we did some problems, right? So friends, at the end of the lecture, the student will be able to understand what is the shear stress and the shear strain, and the shear modulus and bearing stress, and we will do some problems. Okay. So things is what I want to tell. This is already we studied in the strength of materials in the third semesters of mechanical engineering. But still, this is just a glance. This is just introduction to the machine design, and we will cover in the introduction chapter. Okay. So friend, what is the shear stresses? Shear stresses, what is the shear stresses we will study here, and the shear stresses, and what is the shear strains. And we know that whenever a body is subjected to equal and opposite forces acting tangentially across the resisting section, as a result of which the body tends to shear off the section, then the stress induced is called the shear stresses. Means it is calling the it is when a body is subjected to equal and opposite forces acting tangentially across the resisting section, as a result of which the body tends to shear off the section. The stress induced in such a scenario is called the shear stresses. Just shear stresses is equal to tangential forces by resisting area. Just to see in the diagrams, here what the revert 1 2 plate, this is plate 1, this plate 1, and this plate 2 is connected, assembled by the riveted joint, and we are applying the loads P here and a pulley here. Both are in tangentially, means the load is acting the parallel to the cross section. This is the cross section. So resisting of this rivet this is the cross section. This is a cross section area. the load is acting at a parallel to the cross sectional area or tangentially. Then this what will happen? This will be shear off. This will be the shear off. Shear off means it will become two pieces of the rivet. And this scenario, this is, see, if you will apply the load here, it will apply it here. See, this rivet will be shear off. This will be two pieces. In this scenario, the developing the stress is called the resisting stresses. Due to shear resistance, the rivet will be two pieces. Okay, so it will become a single shear or double shear depending upon the type of rivet joints. We'll see that the shear stresses is equal to tangential forces P divided by resisting area here. If you will taking the P is equal to the applied load and resisting area is equal to pi by 4, the area is parallel to the applying force, the pi by 4 d square. So resisting area is 1 here. So area is equal to 1 time of pi by 4 d square. This is resist. The unit is equal to Newton of mm square, the same of the tensile stresses or compressive stresses. Okay. Now we'll see this in chapter. Just to see what is happening here, that you see this in this connection here one plate is there and it is a rivet. It is a riveted joints, right? It is a riveted. Okay, this is a riveted joints. Diameter of the rivet is P. Due to this applied load P and this applied pressure, it will be shear of two pieces of the rivets. Okay. Okay. Due to this one, the stress is due, that is called shear stresses. The shear stress is equal to tau is equal to P by A is equal to pi by 4 P by pi by 4 d square. This area of the rivet is equal to pi by 4 and 4 will go to top. So 4 P by pi by 4 d square. So this is one case 1. This case 1. Case 2 will study here. What is happening here? This is one plate. This is one plate, plate 1. This is plate 2. This is two strap. Okay, supporting strap or strap 1. This is strap 2. All together, this rivet is assembling together. See here, first the plate is there and a plate, first the assembly, this one. Then after that, and above this one strap, and here one of strap also connected here, and here we are applying the loads P. Due to this applying the force, here what will happen? The plate is there and this is the parallel to the cross section, parallel to the applied load. This is tangential area or that is cross sectional area 1 and this is subjected to. Here it will become the resisting area is this one. So if you will see here, each of the rivet will become 3 pieces. Here 1, here 2 and 3 pieces. Just you see 3 pieces. There are 2 pieces. Here become 2 pieces, right? 1, 2 pieces. Here become 3 pieces. But the resisting area will be 2 times. If you will apply load and it will become here, it will go here fail, it will become here fail and due to this one. So you can tell that the resisting area is 2 times here. So if we will consider only one part, So P by A is equal to pi by 4 d square. This is one resisting area. Then this is a 2 resisting area double shear. So that we will tell that it's 2 times. So 2 times pi by 4. We have to see a machine design. You have to see only the resisting area. How many resisting area? Which is the resisting area? Here the shear force is acting tangentially, and the 2 cross sectional area is coming into picture. That's why it is 2 times the cross sectional area. So P 2 cancel. So it will become 2. Top it will go 2P by pi by 4. So if you will see a shear stress is 4P by pi by 5 d square. Here shear stress. So shear stress developed here is equal to more 2 times than the double shears. Okay. Now just to see, because of this is called single shear. Because of single shear, it will become 2 pieces. Okay. This single shear because of like this. I will draw here. Because of this one. Yeah. Because of like this. Because of like this. This is called single shear. This is called single shear. This is single shear. Single shear. This is a double shear. This is a double shear. Okay. Because of the single shear, it will become 2 pieces, and double shear it will become 3 pieces. Just to see, this is single shear. Okay. Double shear, it will become 3 pieces. Pin in the specimens. Okay. This will be subject to like this. So because of this, because of shear stresses, there will be induced the strain is called shear strains. Okay, the stress induced in that is called shear strain. So you know that if suppose this is a bar, this is a block, you are applying the tangential like that, it will go like this. So what is happening like this? It will be distracted like this. Okay, so this is called phi. The angle is called phi. So this is L. This is length of this one is L, and this is how much deformation is happened, del L. Suppose the shear strain is equal to del L by L. Like that we calculated the strength of materials. Now that is called phi. Phi is equal to shear strains. Okay, the angle. So this one is there. Now here what we will do? Shear modulus. What is the shear modulus, or the shear modulus or the modulus of rigidity? Is similar to the Young's modulus. What is the Young's modulus? The Young's modulus is the stress is directly proportional to strain. Okay, that is Hooke's law is state that the shear strain, the tensile strain is directly proportional to longitudinal strains. The proportional is equal to, if we will remove that E is equal to stress by strain, E is equal to Young's modulus. It is the ratio of stress to strain, the direct stress to linear strain. Here similar the shear stress is found that it is found that within the elastic limit, the shear stress within elastic limit, if you will make this one shear stress of y axis and shear strain will plotted x axis. Okay, then it will show the within elastic limit the shear stress is directly proportional to strain. Shear stress is directly proportional to strain. If you will remove, it will come the C time into phi. C is equal to C, or that you can tell that G also you can using. So C is equal to shear stress by shear strain, or you can tell G. G is equal to also modulus of rigidity shear stress by shear strain. Okay, so in that way we can do that. So similar things here is the shear stress is equal to proportional to shear strain, and tau is equal to C times phi. C by tau by phi is equal to C, and C is equal to shear stress and phi is equal to shear strain. C is equal the constant proportionality is known as the shear modulus, or that is equal to modulus of rigidity. This is equal to modulus of rigidity. The unit is same of shear stress unit, or that okay, shear stress is the Newton per mm square, and the unit of the shear stress is equal to same thing mm square, since strain has no unit. Okay, and here that I has given here some, you just see that some of materials they has given the modulus of rigidity of various C value of the common materials. We can know that steel it is around 80 to 100 GPa. Okay, 8 to 100 GPa. Wrought iron you will see 8 to 90. Cast iron it is around 40 to 50. Copper is equal to 30 to 50. Brass is equal to 30 to 50. Timber is equal to 10 GPa. So friends, this is you can get the design data book. Okay, just I given you note down this formula also. Okay, so friends, we will do here one problems. Okay, what is telling that we will do here some problem. Okay, we will do a solution. Calculate the force required to punch a circular blank of 60 mm diameter in a plate of 5 mm thickness. The ultimate shear stress of plate is given that 350 Newton per mm square. That is not a problem. What is given? Calculate the force required. So force required is calculated. Let the P is equal to force required, right? P is equal to the force required to punch a circular blank. Okay, the diameter of this one is given, D is given 60 mm. In a plate of thickness is given that 5 mm. The ultimate shear stresses of is given that ultimate shear stress, maximum shear stress is given 350 Newton per mm square. So friends, he is telling that how much force you will act like that. So always you see the force P is equal to okay, stress, okay, stress into resisting area, right? You know na, the stress is equal to force by area, you know, force by resisting area, right? Area. That's why it is, you remember that the force is equal to stress or ultimate stress into resisting area, okay? But we can tell that force is equal to, okay, stress into resisting area. So if you know the resisting area, then problem will solve. So now what is coming? He has given one plate like this, okay. Draw the diagrams, then you can get here what is happening here. Draw the diagrams, and he is making that like this, okay. This is making the diameter of the pons circular is d is given, that is 60 mm, and is given the thickness of this one is equal to, is given is equal to 5 mm. So the resisting area is equal to, it will looks like this, resisting area. The resisting area will be like this. So what is this resisting area? This is pi d, okay. This is the pi d, okay. This is the pi d into thickness. If you make this one, the resisting area will be pi d into pi d. If you remove, if you make this length, the circular diameter, if you make to length, what will come? Perimeter will come pi d, and the thickness, it is like a, it will come like this. It is a rectangular. So this is pi d into t. So what is coming? Resisting area is coming pi d into t. So I can write here P is equal to resisting or ultimate shear stresses, okay, into resisting area is equal to pi d and t. Now we can put here pi t has given that, okay. You know that area you can calculate now. Pi dt is equal to pi into, okay, 60 into 5. So how much is coming? That 942.6 mm square. So this is, you can note 350 Newton per mm square is given into 950. How much is coming? Sorry, how much is coming here? 942.6. So it is coming 329,910 Newton, or is equal to 329.91 kilo Newtons. So here the shear stresses units Newton per mm square into area is equal to Newton per mm square. You will cut the unit will come Newton, and you can convert to kilonewtons. In this way we can do the problems, okay. Okay, in this way you can do the problems, okay. Now we'll go one more problems we'll do. What is giving here? Just to see that a pull of 8 kilonewton is transmitted from a x to y through a pin. This one is a pull here, okay. What is happening here? If the maximum permissible tensile stress in the bar, tensile stresses of the bar is equal to 10 Newton per mm square, a permissible shear stress is of pin is equal to 8. Find the diameter of bar of the pin. This is the main thing, is that whenever you are doing such a problems, you should know that which is the resisting area. Whenever the shear stress will act at the parallel to the cross section, and tensile stress will act across the cross sections. So in that way, what is happening? This is one part, okay. This is one part. This is the one part, okay. This is the one part. this is one part, okay, this is one part, okay, and this is one part, okay, this is one part, right. Sorry. Sorry, okay. Now if you will see, and this is the pin, this is the pin, this is the pin. Now what is happening, you are applying the load 8 kilonewton, here 8 kilonewton. Due to this one, what is happening, the here this is the pin, this is the pin, okay. Due to this one, the whatever the pin will be shear off, the resisting area will be this one, the resisting area will be this one, okay. This, due to this, pin will be shear off here and here, okay. Now we will see that what is given, that solution will do that. What is the solutions? P is given, that P how much is given, P is given 8 kilonewton is equal to, we can calculate 8 into 10 to the power 3 Newton, and A is given, and we will ask the diameter of the pin, so diameter of the bar, okay. What is asking, that from the x to y, and the tensile, the permissible shear stress is the pin shear stresses is given, tensile stresses is shear stress is given 8 Newton per mm square, and tensile strength is given 100 Newton per mm square, right, is given. Now find the diameter of the bar, and this is a bar, okay, this is a bar, this is the bar, and this is a pin. So the bar will fail due to the tensile stresses, and the pin will fail due to the shear stresses. So first we will calculate the diameter of the bar. This is the bar is connected, okay, with the pin joints, okay. Diameter of the bar, suppose dB is the diameter of the bar. So you know that if shear, you know it will fail in the tensile stresses. So the diameter of the bar is equal to pi by 4 into sigma d, sigma dB to power square is equal to how much it will come, 0.7854 d2 dB per square. And you know that shear tensile stress, it will fail due to the tensile stress, because the load is acting at this area, okay. This is a cross sectional area like that, okay. It is pi by 4 here, it is perpendicular to the applied loads. So stress is equal to P by resisting area of the bar. So in that connections, tensile stresses is equal to 100 inverse. P you know that 8 into 10 to the power 3 divided by area, you know that 0.78454 dB per square. Now you know this one, you know, and dB you don't know, so you know this you just calculate. It will come dB is around it will come 32 answers, okay. dB, if you will make the square root of that, then you will get the 32. Now the pin will be, actually here what is happening, here the pin will be shear off in the two sides. So two resisting area is there, pin shear off in 2, so it will become 3 pieces, 1 2 3 pieces. So resisting area is 2, the pin will be in, shear stresses will be 3. Just you will see that we will calculate here, what we will do, the diameter of the diameter of the pin. So we know that suppose dB is the diameter of pin, the diameter of the diameter of the pin, okay. Since the P is equal to tensile loads P is acting, the pin will be two sections, okay. two section, one A, B and CD will be section. Therefore, the pin will be in a double shear. It will be in double shears. So the resisting area, first we will see the resisting area. You will know that is enough. Here resisting, shear resisting area, resisting shear area. Okay, shear tangential shear area is equal to here 2 times into area of the pin is equal to pi by 4 and dp square. Then how much is coming around? 1.571 dp to the power square. So now we know the shear strength is equal to pi by area of the pin is double shear. So you know that 8 is equal to 8 into 10 to the power of 3 divided by 1.571 dp. Okay, you can calculate here the dp will be around 25.2 mm. So what you got here, that the pin will shear off by the shear stress, shear resisting area, and the bar will fail within the tensile forces. So diameter of the bar we got the 32 mm, okay, and diameter of pin we got the 25.5 mm, 4 mm. Okay. So now we will see the what is the bearing stresses. Okay, what is the bearing stresses? Okay, this sometimes it is coming. What is the bearing stresses? Localized compressive stresses at the surface of a contact between the two matching parts that relative at rest is known as bearing stresses, or that is called the crossing stresses. This is like a compressive stresses, but the compressive stress is different. The load is there we know that compressive is 2 equal push. When we will apply the applied load to the normal cross sectional area, we are knowing that is compressive stresses. But here it is called bearing stresses. The bearing stress is localized compressive stresses. Bearing stress is nothing but localized compressive stresses at the surface of contact between two members of the machine elements that is relatively at rest. It is known as bearing stress or the crossing stress. How it act we will see here. The bearing stress is a count in the design of rivet joints or cutter joints or knuckle joints. In this type of things, where we are considering the rivet the bearing stresses. Okay, I'll show you that how it is acting. Localized compressive stresses. Okay, we'll consider the rivet joints. The P is applying the loads. In such a case, the bearing stress or crossing stress will be stress at the surface contact between the rivet and plates. How it is acting, I'll show you. Suppose that is the P is applying the loads. This is two plates are connected by the rivet joints, and you are applying the force P here, and T is the thickness of the plate, and D the diameter of the rivet. Diameter of rivet is the thickness of the plate. And if you see here, this is what is happening. If you see here, suppose this is the plate, this is the two plates. Okay, this is two plates. Okay, is connected by rivet. This is rivet. Okay, like this. This is the rivets. Okay, this is connected by the rivet joints. This is rivets. Okay, surface is connected by like this. So if you see this, the localized compressive stresses, here telling localized compressive stresses means the rivet is connected to the plate. The rivet surface is connected to the plate. In this area, this localized compressive stress will develop. If you make the projected area of the D times diameter times the thickness of the plate, this will act like this. If you see like this, D time is the diameter of the rivets. Okay, D time is the diameter of rivet. This is the thickness of the plate, T and D. This is the projected area. That is known as, this area is known as crossing resistance area or bearing resistance area. If n is equal to the number of pitch length in the bearing crossing area, then that will come. Now if you see the bearing, now if you see here, the area is equal to the projected area d times. So if you see, I want to tell you just this, I will cut this pieces like this. If I will cut this I will cut like this. So if you like this, I will cut like this. If you will see here, this is the diameter, this area, just see here, what is this area? This is the actually the diameter, this is the diameter of the rivet, and this is the thickness of the plate, and the rivet is here. So if you see this localized compressive area, this is localized compressive area. So if you make the projection of this one, what will happen? You will get one cross section like that. So D will get, and T, this is the crossing area, or you can the bearing area, okay, like this, okay, projected. So the crossing or bearing area is equal to P is applied loads by D into T into N is equal to number of rivets. Suppose that number of rivet 2 pitch length, then you can tell the 2 times, otherwise D by T. And if number is like the number of shearing area will increase by shear stresses, number of rivet if will shear, resisting area will be double, then you are getting 2 times the area of resisting increasing. Here the number of rivets how many there, then you can multiply this. If you see here journal bearing, if you see the journal bearing, what is this is a diameter, this is the diameter, and this is happening, and this is like a cross sectional area. You will see the D, and this is the length of this supporting length. Then if you see, it will come like this. This is the diameter, but it is like this. You will see like this. Okay. This is D, and the length is equal to this much. So if you see here, this is actually the projected area. If you make it, this is actually the compressive area. You will see this view, okay, this view you will see. Then what is it? D into L. Here it will come the crossing area. It will come D by D into L. D is the diameter of the shaft. L is equal to length of the journal. Okay. Now here what you can, the P into D by L. I already told it will like that. Okay. It will come like this. So this area, this is the localized compressor area. If you make the projected, what will happen? It will come like this one, rectangular. This is one rectangular. Sorry, not straight. Okay, it will come on localized area like this. So this is the length, this is the D. Okay, this is just visualized. So bearing load is stress is equal to P by L into D. Okay, average bearing pressure, we are telling average bearing pressure like that. This is P is the radial loads on the journal. L is the length of the journal contact. D is the diameter, length of the journal in contact. D is the diameter of the journals. In this way, we can calculate the bearing resistance. Okay. Now, friends, we will do one problem here. What is happening here? Two plates of thickness 16 mm thickness jointed by the double riveted joints with lobjet. Double riveted means 2 riveted joints. Okay, 2 rivets. The one rivets, here is 2 rivets. We will see that left joint, and when we will study the rivet joint, we will know the double riveted, triple riveted, single riveted, but like that we will study, no problem. 2 plates thickness is given, T is given 16 mm, double riveted, and number of riveted per pitch length you will get number. A number double riveted, N is equal to 2, you can write here. Okay, find the crushing stresses is asking. Crushing stresses is asking induced with the plate and rivet. If the maximum inside tensile loads, he has given the load is equal P is equal to 48 kilonewton, he has given. So 48 you make into 10 to the power 3 newtons. Okay. Crushing stress is given, you write load, tensile loads, okay, tensile load by crushing area, that's all. So no problem, you can calculate here. What is happening? Since the joint is double riveted, therefore the strength of the two rivets in bearing and crossing is taken. So since it is a crossing, is 2 will be cross, this side will cross and this side will cross. So 2 rivet strength will for crossing resistance will take care. We know the crossing stress between the plate and the rivet is equal to tensile stress P divided by D into, I told no, this D into T, the projected area, D into T into number of rivets. Okay. Since 2 rivets pitch length, 2 rivet is there, so double riveted, number of rivet per pitch length is equal to 2, you can calculate. So 48 into 10 to the power 3 divided by diameter is given, riveted diameter, the riveted diameter is 25, right, D is equal to 25 mm, and T is equal to 16 in number of rivet. How much is coming here? 60 Newton per mm square. Answer. Okay. This way we can calculate. So next, just a second. Okay, this way we have to do the problems. Okay, we'll leave here. Okay, you will do the problems in your home also. Okay, I will do in my own one problems. I can do that. Suppose a journal bearing of 20 mm diameter is given. So journal bearing 20 mm diameter is suppose is given. Journal bearing if you given here, okay, diameter, and sliding bearing is the maximum reaction is coming that, okay, reaction, so force is given that 25 suppose is given Newton. Assume the allowable bearing pressure, so pressure is given that allowable pressure of the bearing, that is nothing but the stresses, bearing stresses we can tell, bearing pressure or bearing stress we can calculate, so 5 Newton per mm square. Find the length of the sliding bearing. You can calculate that. Okay. So I already told that if you like that bearing is there, we can calculate. Suppose correct. I already like that is there. Suppose this is the bearing. Okay. So this is suppose L is a length. This is D is equal to this one. So if you will see this in this problems, what is happening, that a crushing area will be like this. Okay, the crushing area will be like this. You will make the projection. What will happen? This will L and this D. So you know that bearing stresses or bearing pressure is equal to load divided by crushing area, or that is called the compressive, localized compressive area is equal to P L into D, okay, L into D. So you can calculate, he has given P is equal to 5 Newton and P is pressure is equal to 500, suppose he is given like this. L you have to calculate into 25 given the diameter. So you can calculate L is equal to 25,005 into 25, it will come around 20 mm. You can get 20 mm. Okay. In this way you can find the bearing stresses and the shearing stresses. I took these classes around 40 minutes. Next lecture will do that stress and strain diagrams of mild steel, and you know that mild steel is very important. Here that we will get the all properties of this material. It is, you should be a designer, you should know that. Okay. So here I want to conclude today lectures. Tomorrow lecture we will see the stress and strain diagrams and the percentage of reduction of area, percentage of elongation, and I will do some problems. and we will find out what the working stresses, factor of safety, and the selection of the factor of safety, and mechanical properties of the materials, like that. Thank you. We will meet in the next lectures.